again, this is part 2 of section 2.1. We will talk about some basic concepts of a set. So what is a finite set? Well, a set is finite if it has only a finite number of elements. So let's see, example, set B is a finite set because it has only 5 elements. 5 elements, right? So what is an infinite set? Or infinite set just means it has infinite number of elements in it. Okay. Example, the set of natural numbers, counting numbers, n, we talk about a number of times, is an infinite set. Okay. So when two sets are equal, or when we talk about when two sets are equal, meaning that they have identical elements, then the two sets are equal. Okay? So let's see, example 1, 2, 3. The left-hand side set is equal to the right-hand side set. We will use the notation equal to indicate two sets are equal. So notice the order do not matter. Okay. So what is the cardinal number, or sometimes called cardinality of a set? Okay, so this is a rather actually advanced concept. But if a set A is finite, then we can easily define the cardinal number of the set A is actually the number of elements in the set. So that's very simple. Typically, we use n of A to indicate the number of a set. Okay. So example here, set A equals to the set of 1, 2, 3, and set B equal to the set of 3 countries. Then both sets have cardinal number 3, or the cardinality of each set A or B is 3, and we can write this. Okay, so what do we mean by two sets are equivalent? Or this is a little bit different than two sets are equal. So when two sets are equivalent, if and only if they have the same cardinality. So again, for the finite sets, it's easy. If both sets are finite, then the two sets are equivalent if and only if they have the same number of elements. Or in general, the definition would be when there is a one-to-one correspondence between elements of A and elements of B, then we will say two sets are equivalent. So this definition, the general definition, actually works for both finite or infinite set. Okay. So let's look at a quick example. We talk about set D and E both have 3 elements. Obviously, they are not equal, but they are equivalent. Okay, they are equivalent. So what is an example of a two equivalent set, but both sets are infinite? So let me think about an example here. Two equivalent infinite sets. So example, let's see, set of natural numbers, okay, n equals to 1, 2, 3, 4. And what, let's say, set of z plus. A plus just means a set of all non-negative integers, 0, 1, 2, 3, 4. Okay, so in this case, you know, you can find a one-to-one correspondence between n and z plus. So in this case, n is equivalent to z plus. Okay. Another example is, let's say n not equivalent to the set of R real numbers. Okay. So because you cannot find a one-to-one correspondence between elements in N and elements in R. So I want to quickly talk about that. So equivalent sets, equal sets, those are two different concepts. Okay. So let's see. Let's look at these two examples here. D is a set of A, B, C, three letters. And E is a set of, apple, orange, pear. And because both sets have only three elements, so set A and B are equivalent. However, set D clearly is not equal to set E. They talk about different objects. So we can get this relation here. Two sets are equal, then obviously they must have the same number of elements. Then therefore they must be equivalent. However, the other direction, two sets are equivalent doesn't imply they are equal. Okay. So one-to-one correspondence, this is a very rather abstract and advanced mathematical concept. What do we mean? There is a one-to-one correspondence between two sets, and what are the examples? Okay, so let me give this couple of examples here. So let's say set A, let's say 1, 2, 3, just contains three elements, and set B, let's say contains three ships. Okay, and we can, and then we can find one correspondence, one-to-one correspondence relation between elements of those two sets. So this is an example of one-to-one correspondence. So let's see another example. Let me just still use this 1, 2, 3, and B, let's see, equals to still those three sets. Okay. However, I'm gonna associate 1 to that, and 2 also equal to that, and 3 equals to that. Okay, so the association is defined by me. Okay, so then this is not a one-to-one correspondence. Okay, so let's see. Here's another quick example. Here we got set S is set of 4 states, and set C is set of 4 cities, and then you actually, because the two sets, you can find a one-to-one correspondence between the sets S and C. Example, a quick example here is that you just match a state to a city, or you have some meaningful matching. You match the capital city to a state. But the point is that there is one-to-one correspondence between the two sets. So what is a null or empty set? Well, a null or empty set, by the way, they mean the same. Okay, they typically are used using this symbol or this symbol to represent a null set. So let me write this. So this notation means that there is no element inside that. Okay, so that's represent an empty set. So example here, Notice the first example here, this is not an empty set because it has one element in it. This set here is also not an empty set because it has one element, 0, inside it. So what is a universal set? Universal set, it just means overall the entire set under discussion. Okay. Example, we can define our discussion only restricted to all AUM students. So underlying universal set, we use U to denote it, is a universal set of all AUM students. And you can have two subsets which are not a universal set defined. For example, U1 is set of all in-state students, and U2 is set of all out-of-state students. So that's the concept. Okay, so typically we would draw something like this: a universal set. Typically we draw, you see, a large rectangle, and then we got U1 and we got U2 inside it. Okay. So here's another example. If the universal set is defined as only restrict to the first 10 natural numbers, then that's your universal set. So